Hello. Hello. Check, check, check. Check, 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 check. Check, check, checkity, check, check. That's sweet. It's recording, so here's all my checks. Hello. All right, see, we got a couple of early adapters coming on here. We'll wait a few minutes to get started. I believe you should be able to see kind of the title page here, but I'll be honest, this is my first time using this software as well. All right, looks like we got a bunch of participants joining here. Is everybody able to hear me? And I guess the way to probably signal that is via the chat box in the Baja SAE virtual meetings. Perfect. Loud and clear. Thank you very much. We'll wait probably a couple minutes here while folks filter in and join. Hopefully everything stays pretty quiet on my end. I have 4 little kiddos that are outside playing, and my wife has promised to corral them and keep them out there. So if you hear horrible screams, it's not like there's an exorcism going on here. It's just kids beating on each other, and they need to get shooed back out of the house for this hour. Yep, for sure, kids being kids. So as we go through this too, if you come up with any questions that you want, go ahead and drop it in the chat box there. I anticipate having some time at the end of this to answer those questions, but drop them in the chat box and I'll try to answer them as best I can at the end. And I may, depending on how applicable it is, or if it's something I'm going to get to, I may answer it just straight away right there as well. So feel free to use that chat box that's on the virtual meeting website there. So pretty fun topic. I submitted that poll there. It looks like we've got kind of what I figured would be the heavy hitters of things that folks struggle with the most. The tuning and making it run the right RPM on upshift and backshift. About half of the presentation will be dedicated to that. And that I know that is something that everybody struggles with, as well as that understanding how the contraption works also can be a bit of a mystery. We paint our covers black, and so at Polaris they're all nylon molded black, and so it's really the black box. All right, well, we're a couple minutes past, so I think we can probably go ahead and get started here. Well, first, welcome to the seminar on Wizardry and Witchcraft, conjuring the most out of your CVT system. And I'll try to leave that metaphor sooner versus later on it, but it really is a lot of mystery I get that surrounds the CVT system. And it's not just in Baja, it's in industry. It's at like Polaris, who has had CVT transmissions since really the company came about and snowmobiles and began making higher performance snowmobiles in the early 60s, but still there's very, very little understanding about CVTs outside of the core CVT system. I'm Amery Kuhl. I'm a CVT staff engineer at Polaris, and welcome. So a quick little bit about me. I attended the South Dakota School of Mines and Technology from 2005 through 2009, getting my bachelor's of science in mechanical engineering. More recently, I also got my master's degree in engineering management from South Dakota School of Mines. And my time there was extremely heavily involved in Baja SAE. I attended competitions from 06 through 2009, and I was the underclass captain in 2007 and 2008. And some of the more noteworthy things there is we did manage to beat Jason Fields in 2007 and 2008. He was a member of the senior car, and you can see those results over there on the right. The one asterisk that Jason was a little miffed about is I did technically drive the senior car in 2008, where we wound up placing at 6th. But I'm not the guy that rolled it in the endurance race that caused us to get 6th place either, Jason. So that'd be my small Baja claim to fame. After college, I worked in agricultural drivetrain in 2009 to 2010 at John Deere. And then I've been at Polaris ever since. And I did bounce around a little bit. Polaris has an engineering development program where you rotate through different functions in the company, different locations. And one of my more favorite ones in that rotation was the time I spent as a snowmobile CVT and driveline engineer. And that kind of served as a launching point for, I really liked CVTs, and I was a driveline guy kind of to begin with on it. And so after that engineering development program, I moved into ORV CVT, and that's where I've been since 2011 until current. I kind of comically like to say I do make a lot of clutch decisions at Polaris in my role as a CVT engineer, but really I love Baja SAE, and now I get to do really what I love at Polaris. So this is a very, very, it looks like some people are saying they're showing waiting for the host to join the meeting. Is that a common thread for others, or is that just a couple of folks? Common, need to join the meet, need to start the meeting. How do we, so is that in the chat box, folks, is that a common thread for folks that are, okay, some are able to join successfully. I guess my comment to those who are struggling would be probably try going back and finding it through the virtual event site and refreshing or clicking again. It sounds like it's somewhat isolated. So I guess continuing with some common CVT terms, this is a pretty nasty looking list, but there are some of them that are pretty important as we go through this presentation. We talk about engagement would be when the clutches just first start to close on the belt and start to transfer torque. So that's when you initially drive away. You need that high enough that you don't creep, which would be like unwanted movement just above idle, but not too high. Otherwise you start actually losing the ability to drive away, and you can cause spin burn of the belt because there's so much relative speed between the primary clutch and the belt at engagement. Stall speed is a time when you're at wide open throttle and there'll be a transition where you go from dynamic COF on the belt to a more static or quasi-static coefficient of friction. You'll see a transition in the upshift slope. We'll see that a little later. Upshift would be changing CVT ratio as the number is numerically getting lower, so you're accelerating from a lower speed to a higher speed. And upshift RPM goes hand in hand with that, and that's the RPM that the CVT shifts at. And normally we reference that at full throttle, and that typically is near peak power if you want to have the maximum performance or best acceleration on it. It's not necessarily the speed at the very top speed that you're running at that the engine is running. It's as it's still transient and the clutches are shifting. Back shifting would be when ratio is changing to a lower gear ratio. That would be a numerically higher number due to an increasing road load or an increase in torque being transmitted to the system. So it's the clutches going the opposite direction they would be when you're accelerating from a lower speed to a higher speed. Overwind can be confused with upshift RPM. So when you run out of gear ratio in the clutches, they're in the furthest shifted out position. RPM will then begin to increase, just like it would with a typical mechanical transmission. And there'll be a direct relationship between engine RPM and vehicle speed, both increasing once you go into that overwind condition. So there's just no more available travel or available ratio left in the clutches. Backshift response is it can be qualitative, typically is how people describe it, but you can definitely put numbers to it, and you need to put numbers to it to get a better idea of the small intricacies between different cals. But that's going to be the speed at which the CVT goes back to the desired operating RPM in an off throttle event. So you get out of the throttle, RPM drops. When you get back into it, how long does it take to get back to the target wide open throttle upshift RPM? We talk of underdrive as being a condition where the CVT is below a 1-to-1 ratio, and the max underdrive would be the low limit of the CVT reduction. Typically, that's somewhere between 2.5 to 1 to 4 to 1, and that's the most mechanical ratio that you can get in the CVT system when you're starting out. Tail force would be, if you've got a flyweight style clutch, is kind of where it stems from. It's the amount of force that the tail of the weight would be producing, or at full ratio that the weight is using. We say it because the tail is flipped out, but it also applies to ramp roller style clutches and puck clutches. It's just, you would use it to say we need more tail force, maybe for example, as though engine RPM is too high when the clutches are nearly shifted out. Initial force would be just the opposite. It's the force being applied by the weights right away when you're starting out. Overdrive, pretty self-explanatory there. Ratio spread is one thing that there's a ton of opportunity for in most CVT systems, and that's the max underdrive ratio divided by the max overdrive. And so the way to really gain with the CVT system is to maximize that ratio spread. You can always gear your gearboxes, or your could be a belt case or a chain case. You can gear those deeper, numerically taller, and exploit CVT overdrive to gain additional draft force starting out. And really one of the biggest opportunities is to pull more overdrive in CVTs. When you start dividing by those low overdrive numbers, you really start increasing that total ratio spread that you have to work with on there. And you can think of that as going from like 4-speed transmissions in cars up to the 6-speed, 8-speed, 10-speed type automatic transmissions that we have now, where there's just a lot more spread in the range of ratios. Tension ratio, we'll go into great detail on that later on in this presentation, but that's really the ratio of tight side of belt to slack side tension. Light is going to be a word to describe operating RPM being higher than desired in upshift. Heavy is just the opposite of that. The engine is lower RPM than desired. top end, big end, final shift ratio, they're used to describe, you know, the RPM or the characteristics of the vehicle as you're approaching the max overdrive condition. And bottom end is more to describe, you know, low end just starting out near the minimum underdriven ratio of it. And see, I got tension ratio twice on there. It's that important. So types of transmissions. There's a whole variety of CVT transmissions, way more than just the rubber belt that a lot of folks are familiar with and are common in sleds and ATVs, Baja cars, mowers, etc. Another one that's, you know, very similar to that friction drive style is the dry hybrid belt, and that's shown on kind of like the upper right-hand side there, and that's generally in lower power applications. There's a company that uses it with a supercharger that they have with a CVT-based supercharger, but you struggle to get a lot of power and torque transmission through that style of a belt. Traction fluids have been really heavily in development the last 10 or 15 years especially. There's a bunch of variations on that, from the toroidal design, which is kind of showing that yellow roller setup, to New Vinci, which is the kind of ball style shown in the center with the red balls on it. Then of course there's steel push belts, which are found in automotive applications, automotive cars. Like Nissan has a push belt style of technology where the belt is a pushing steel member. There's also chain, which is kind of more like the rubber belted CVT system, and that relies on pulling, and that's kind of shown there on the left. And finally, there's like cone drive, which is used in really pretty light duty applications. It's seen some service in lawnmowers. There's some Lego cone drive type of things that are out there, but they're not really that reliable at high torque transmission, don't really lend themselves to long-term durability. Fluid drive, the hydrostatic, has been around for quite a long time. International Harvester kind of really staked a claim to that in the 1960s. And then there's the hybrid. A lot of the tractors that have CVTs and IVTs are hydromechanical, where they have a DCT type transmission, and then they speed up or slow down one of the shafts on that DCT style using a hydro motor. So most of the torque and most of the work is being done by mechanical, and there's just a small speed up, slow down by a hydrostatic drive. Then there's of course the dual power source, where you get your automotive electro over mechanical systems. The parts, you've got a drive clutch mounted to the engine typically. You'll have yourself a driven clutch, which is mounted to the transmission input shaft or jack shaft. The belt, which is what is responsible for transmitting torque from the drive to the driven clutch. And it has a very difficult task associated with it. And then finally, we've got the clutch covers and the ducting in the CVT system, which primarily cools it, but also in the event of a catastrophic failure or even belt failures, it's responsible for containing all of the parts and preventing further damage to other systems on the vehicle or operator. So stepping into each of these, a lot of opportunity on belts. So belts are made up of cord and rubber, basically. There's a high strength tensile member in cord, typically polyester, carbon fiber, or aramid. And the one thing to note, I would say here for Baja type applications, would be that carbon fiber is likely not your friend. It's extremely abrasive to sheave surfaces. So those of you struggling with wear of sheave faces, that carbon fiber cord is extremely aggressive and abrasive on aluminum. You will struggle with wear and grooving associated with that carbon fiber cord. It's also been particularly difficult to get to adhere to rubber, and Gates has made some huge strides in that respect, and they're getting it quite a bit better. But the high modulus of carbon fiber makes it hard for a belt. When the belt rotates, any amount of deformation due to like getting pinched on it, and you can picture it kind of like dishing, that loads the outer tensile member, and that high modulus of carbon fiber is definitely not your friend in that respect. So as the belt deforms, you wind up with just that outer cord taking the load, and the higher the modulus of the cord, the more load goes through that. Now, carbon fiber is very strong too, but it has to take a lot more load. And in general, smaller cords can make belts a little more flexible at the expense of cord adhesion. For the old Briggs 10 horse, probably any one of those, polyester, carbon, or aramid, will be just fine. For rubber materials, there's 3 main players on there, and the thing that's probably the best for a Baja would be this first one, chloroprene, which is pretty common in power sports. The majority of power sports belts are chloroprene, and that's just kind of a fancy generic word for neoprene. It's fishing waders essentially, but it is a material that's great in wear. It's moderately priced, and most important is it provides very consistent performance over wide operating temperatures. And it will degrade above about 230 F, but it will function very, very well until 270 F, and you can push it higher than that, but you start to see difference in performance. In contrast, some of the others, HNBR and EPDM, are poor in wear. They're not as good in wear, but probably most importantly for Baja type applications is the inconsistent performance. The upshift RPM will vary wildly depending on if the belt is cold or if it's hot, and chloroprene is by far the leader for running the same most consistently throughout a wide variety of operating temperatures. It's the most forgiving, easy to clutch, easy to calibrate. The only reasons for those other ones would really be if you're looking to push temperatures consistently above 300 F or close to 300 F on the side face temperatures of the belt. If you're not doing that, and we shouldn't have to with the old Briggs, absolutely chloroprene is the way to go. For construction, and I refer to construction as like the thickness of it, the shape of the teeth, the cog profiles, and the general is choose the most flexible belt that does not have issues with cord adhesion or deformation failure. So if you're not squeezing it so hard it's deforming and popping cords out the side of it, which is not a typical Baja type of failure, you should be using the thinnest belt. And a lot of that work comes from kind of experience. There isn't a outstanding calculator that you have to decide, just which belt do we need for a 10 horse engine, because there's a lot that goes into it, sheave angles and the clamp loads on it. But you want flexibility is kind of the name of the game for efficiency. The bottom or inner cogs are the ones that do all the work. They support all the compressive loads of sheave, clamp, and pinching that's going on. And they also bend as the engine is going through torque pulses. They're going to be like little beams and bending and take quite a bit of deflection to them. They really do all the work. Top cogs, they support the cord, but their real only purpose is to make sure that the cord material is bonded on both the top side and the bottom side to gain better adhesion. They add very little to additional stiffness in the belt. They really don't do squat for heat transfer and ejecting heat. It's not like fins on a radiator. Air doesn't really get to them. And so there's slight improvements in transverse stiffness, but really the main benefit of top cogs is just so that there's enough there to support the cord. If you're looking to improve performance, that's probably one of the areas that you can gain on, is by minimizing top cog thicknesses, top cog heights. And keep in mind, belts flex a lot. So like the small difference in stiffnesses, you may think it's not a lot, but know that hysteresis is extremely significant. Some Polaris belts bend at over 160 Hertz. And so slight changes in that stiffness can make big difference for efficiency. On the analysis side of things, everybody really needs to have a calculator for sizing belts to get the correct center distance spacing if you're using an off-the-shelf belt, or getting the correct length of belt if you're doing your own type of belt, getting the right length in there, making sure that you hit all your ratio and speed targets. And don't forget to account for belt deformation, and also the fact that slip is real on V-belts. It's common to see 5 to 8% even slip on high power V-belts, and that's not like gross slip, that just is inherent in the system. It's equally as important to develop a nice driven clutch calculation tool to understand belt tension and compressive forces, and you can go in and model and see what that deformation and dishing looks like, and knowing modulus of cords, get an idea of how much tension is in those cords to see if you're going to have be suspect to cord popping issues or not. But in general, the most flexible belt that doesn't have deformation failures is what we should be running. One question on cord adhesion. So the cord material is treated with a bunch of different proprietary adhesives to get it to stick to the rubber. And when we talk about cord adhesion, it's cords that actually, because of the tension, they share a lot of the load on it. And you've got a really high stiffness difference between the rubber belt material, the compression material, and these like aramid or carbon fiber cords. And if you don't have adequate adhesion in that, that initial interface between a very high modulus cord and that low modulus belt, you'll see what we'd call adhesion failures, where the rubber just rips off of it. And so getting a really, really strong bond between that cord and the rubber is very, very important. And so important that we need to have good adhesion on the top and the bottom side of the cords and making a nice sandwich out of it. So drive clutch really acts on the belt. It moves and adjusts the pitch diameter of the belt. You can engineer different angles of it. Shallower angles are generally going to provide more available ratio because you're limited by total displacement. Shallower angles also minimize dynamic misalignment. That's as it's running and you're shifting, the drive has to travel much further axially than the driven does at initial ratios, and the driven eventually catches up, causing the belt to kind of, it migrates inward towards the engine relative to the driven clutch, creating that dynamic misalignment that you may say it's aligned properly at idle because it's not touching either sheave. But as soon as the clutch starts shifting, that belt tracks in further until you get into overdrive, and then it starts tracking back out. The sheaves also provide a means of cooling. Spring is really there just to tune engagement with initial preload, and it subtracts weight from the weights, the pucks, the rollers. Those weights and spider rollers, ramps, pucks, they're responsible for applying the force. They're the driving function in the drive clutch, but also keep in mind the drive is really just it responds to the driven, and we'll get into that in a minute. It's the dumb clutch of the two, despite it looking quite more complicated. In flyweight clutches, that characteristic upshift curve is going to be dominated by the profile, that outer shape of the weights. And if you've got a ramp and roller, it's going to be the profile of that ramp that's in there. And in a puck style clutch, it's going to be the shape of the cover that drives whether RPM rises over time or drops over time. And that's the most impactful thing when you go into tuning CVTs, is that to get target upshift RPM is to play with the profiles. Analysis wise, understanding those flyweight roller, puck loads, and belt contact patch and stiffnesses are absolutely critical to modeling primary CVTs. And a lot of these spreadsheets, they wind up being only a couple spreadsheets that talk to one another on it. The place to start is a calculator where you can run through, be it SolidWorks or ProE, whatever your CAD software is, a sensitivity analysis or similar, to get an idea of what the reflected force is going to be from the weight in various directions on the cam follower setup, or if you get pucks, it's the force on the cover, to optimize the strength and the weight really of parts, so that we're not really overbuilding, and also that we're not, getting into issues with stiffness or fatigue issues. Typically our worst cases are going to be, an overspeed condition, like a belt fails and we exceed the rev limit momentarily, that min ratio at wide open throttle and max ratio at starting throttle. But we can't forget about fatigue either on it. And on some things, like the spider is probably the most challenging thing for fatigue in all of CVTs on there. And that's because it's usually nearly fully reversed. And I haven't measured a Briggs, but I suspect that with a single cylinder, it's nearly fully reversed and sees alternating torques that are on the order of 5x what nominal torque is. So it's way more than 13.5 pound-feet of torque that's going through that spider and through that clutch, because of that dynamic nature when the engine fires and the inertial effects of starting and stopping a heavy piston or rotating assembly. So a lot of moving parts in a drive. Fatigue is one of the major challenges. The driven, kind of a lot of the same thing applies to, it acts on the belt, shallower angles or more ratio. One thing to note, there typically is on a driven clutch a 1 to 3 degree angle difference between drive and driven sheave angles. And a lot of that is due to just minimizing that dynamic offset that you get, because the drive has to travel so much further axially than the driven does until you get into overdrive, and then it flips. And that's just taking up belt length and diameters, and you get really a pretty significant amount of misalignment where that the belt is at an angle. And why that's bad is our old friend cord pop and cord adhesion rears its head. That misalignment causes one cord and edge cord to be loaded harder than the rest of them. And so it puts extra stress into that belt. So anything we can do to minimize that offset and minimize cord loading, it lets us get away with thinner and more flexible and lighter weight and less costly belt. So we're really trying to minimize the stress on the belt is the name of the game. The spring in a driven clutch does do work directly on the belt. So it's going to provide a constant force independent of road load. It has to provide adequate tensioning to prevent shuffling on decel and belt inversion. So one thing that can happen is you let off the throttle and you're slowing down, and the weird dynamics that go on when you lose tension in that belt are enough where it'll invert and flip inside out or upside down. And so we need to make sure we're controlling the belt well enough with tension that it's not getting into that condition. And spring loads, when it comes to calibrating, they're pretty insignificant at low underdrive ratios, but they may dominate tension at overdrive. If there's a takeaway from this whole presentation, it's start with the helix. The helix is the single most important thing about all of CVT calibration. Everything else is a resultant of where the helix lands on it. The only thing that sets tension in a CVT system is the driven clutch. The drive just responds to it. And we really want to maximize tension ratio without generating gross belt slip on there. So on the analysis of driven clutch side of things, it's a clamp force and belt load sheet is critical to designing the driven clutch from a structural perspective to know what kinds of forces are at play. And also calculating that tension ratio and verifying the slip behavior will allow you to minimize that tuning time to get to the proper calibration. So for John asking about the Ouija board, it starts with the driven clutch, and the Ouija board would be an Excel sheet that describes belt loads is where I would start with that. Obviously, spring stress calculations are important whenever there's a spring, and making sure we're not overstressing or overcompressing springs. And as well as critical speed and whirl is a very common concern. In OEM drive clutches, this is usually the limit, whether it's a Polaris or a Can-Am or an Arctic Cat. We can't really spin driven clutches any faster than we can without exceeding critical speeds on it. And it's more than just root K over M. You do have to run it in a model with an inertia tensor on it, because the inertia is extremely impactful on this as you look at that whirl at high speed. Good place, question here is, where's a good place to find literature or equations to start building an Excel sheet? There, I believe it's Daco has some books published on it, and it's not specific to CVTs. Most of the work that's been done for belt tensions and where we developed ours from are from Daco books published in like the 1960s for agricultural transmissions. And it's a CVT belt is really just a V belt that runs at some different angles, and it can vary pitch, but it's not anything smarter than a V belt. Covers and ducting, I'm going to kind of breeze through this because of the importance on Baja cars is lower on this. I will say that CVTs are very, very poor pumps and very sensitive to restriction. It only takes 500 Pascal of restriction to make a very measurable difference on flow, versus engine side, you can often get away with 5x this amount before you start impacting power. So low restriction is the name of the game. In general, volute geometry in covers gets you the most flow. Air wants to enter at the center axis and then flow through a volute to a larger radial diameter. And while more flow doesn't necessarily mean they're better at cooling, you can have a lot of flow but not effectively cool the belt. It's a lot easier to work backwards and get additional belt cooling by choking and manipulating flow than it is to try to get more flow when you have a very compromised or choked system. It's hard to get flow. we'll start with a lot of airflow, and we can definitely always choke it down. Sheave fins optimization can definitely be done here with regard to fin count, height, curvature, etc. And analysis is very, very troubling on this. Getting flow analysis is good. What you really want is heat transfer, and that is probably one of the most challenging things on a vehicle to understand well, because you're combining a CVT and a thermal model together on it. And you may say, like, you know, we don't really care about CVT temperatures, belt temperatures. We don't blow belts, so to speak. But that performance degradation in the endurance race is a real thing on Baja cars. And, you know, the chloroprene-based belts helps for that, but all that performance degradation is not completely due to the car is heavier because there's mud on it and the Briggs is hot. There's we're getting extremely high belt temperatures on Baja cars just due to, you know, pretty generally poor cooling. Clutch boxes are sealed up very, very well, and there's just no place for that heat to go. All right, probably why everybody is here is calibration and tuning. So for Elizabeth Bowen, there's no object is mysterious, the mystery is in your eye, but she also has never attempted CVT calibration either. But I will say that CVTs generally do perform pretty quickly. I got a question from a fella on here about what should the working temperature be, cooling target for the CVT system. And I would say that goes back to really the temperature material of the belt. So if you can have a belt material that can withstand 230 degrees, you should not be getting much hotter than that in general when you're driving the car. If in your worst case up a hill, an endurance race, high duty cycle applications. Chloroprene is pretty consistent clutching up to 270 degrees. You can get away with that, but you need to be sticking, you know, no higher than that 270 degrees. You are damaging the belt at that point, but it behaves pretty well then. Resource for the Excel sheets. It is an old Daco book that I purchased. It's no longer in circulation. There are some copies on not copies, but Google, I believe, has some scanned images from that book. It does show up fairly frequently on eBay that you can get it from. But there is also, like, your machine design book likely has calculations for tension and V-belt drive systems as well. It's not, don't go looking for CVT specific information. You'll likely fail. Like I said, a CVT is just a V-belt drive system. It's not, DAYCO is the Daco. So the meat of it, there are lots of assumptions in CVT calibration and tuning, and it can be challenging, especially if you don't know exactly what's going on. The most important thing is to start out with a decent base on that, and still the fastest way to get there is to try to get as close as you can to maximizing the tension ratio in the system. And that's Excel sheet, your calculation tool, for determining belt clamp and the torques in the system is critical to getting off on a good foot and getting to an optimal system quickly. When we talk of tension ratio, it's really the ratio of that T1 tension on the top to T2 tension on the bottom if the engine is rotating in a counterclockwise direction on there. And at varying ratios, that allowable tension ratio is going to change. As you approach 1-to-1, the tension ratio limit is the same between the drive and the driven. A common misnomer is going to be that CVTs are most efficient at 1-to-1, and that's really only true if you're optimizing tension ratio and belt bedding hysteresis is significant. Otherwise, it may be something very different than 1-to-1 if you're consistently overclamping the belt. And so that 1-to-1 isn't magic. You can have a very, very similar within a % of efficiency across a very, very broad range of CVT ratios, from like 2.5-to-1 to 0.7-to-1 can be within a couple % of one another for efficiency. It isn't like 1-to-1 is just this magic number and you gain a bunch of speed on that. It's only if you're optimizing tension ratio. Why we optimize that is if you're running at lower than optimal tension ratio, you'll get excess heat due to overclamping and hysteresis of the belt. It's flexing a lot. You're wedging it into these sheaves. And every time you deform that rubber, every time it has to get pulled out of those sheaves, there's work being done. And so running as low a tension as we can minimizes all those hysteresis losses in the belt. However, running at higher than optimal tension ratio, you're going to get gross belt slip and melted aluminum on there. And we'll show that in a slide or two here. So it's only after you've optimized or nearly so tension ratio, that's when you start getting the thing to run the right RPM. And all of that work to get it to upshift at the right RPM happens in the drive clutch. And this is where your force balance spreadsheet is useful for getting this at least close the first time, so you don't have to come up with 20 different helix combinations to optimize tension ratio. You can do it in 3 or 4 or 5. And really, you should be able to get pretty close without too many. And keep in mind, the drive is really just, it's a dumb clutch, and I'll talk about that a couple times too. The fact that if you have something not running the right RPM, but you know the force that the flyweights or the ramp rollers or the pucks are producing on it, the drive is just F equals mr omega squared, and you know the omega, so you can engineer a force curve back that would be the correct RPM everywhere. If you've got, you know, the worst upshifting runs, wild RPMs throughout, it's high and it's low and it's high again. If you know the RPM as a function of clutch ratio and drive displacement, and you know what the force was for an RPM of those weights or ramps or pucks, you can go back and just with that squared relationship know exactly what the force curve needs to look like in order to be spot on. The only other thing on correct RPM is you need to know what you want, what the correct RPM is. And numbers have varied wildly from 2,800 to 3,400. Depends on valve lash and which Briggs you have. And you need to be at peak governed power. It's not, the published literature would say the Briggs is peak power at 3,800 and climbing, but because of the governor, that isn't what you get. So speaking of the driven clutch, this is where we're going to start. Our goal on this thing is going to be to get, you know, the least amount of belt tension to prevent gross slip as we can. That model is critical, and what I show here is, this is for one of our Polaris vehicles. The orange would be the actual tension ratio that we get from the helix, and it departs, and there's reasons for that a little bit. The driven clutch starts out where it could support a very high tension ratio, and then when you get to 1-to-1, that's the point where the drive and the driven cross over, and they have the same tension ratio requirement. In the drive, it can handle a higher tension ratio, you know, all the way out. So at one point at that knee in that curve would be where the driven becomes the critical tension ratio in the system. And exceeding that can cause, like, this is that melted aluminum. This is a driven pulley at peak overdrive. And as we were stepping into that, we were okay unless we were in this, you know, max overdrive condition. Generally with helixes, the tension ratio that you're producing is kind of always increasing. So you need to have a little bit of margin on that tail to prevent this aluminum melting. And that can happen fast, on the order of a few seconds. That type of failure can happen. So when you're in the hunt for being optimized, very minor tweaks are acceptable on this tension ratio. And you want to get close, really close first, and then make some minor adjustments to it where you're to depart further away from what that idealized line is. Generally, shallower helix angles and weaker springs are going to increase the sensitivity to road load. So make it respond better as if you get into the throttle, it backshifts quicker. If you start going up a hill, engine RPM will rise faster than it will if you get there with a lot stiffer springs. The other benefit of having shallower helix angles, so shallower helix angles are going to be producing, you know, more clamp as a function of tension, is they lower belt temperatures and reduce fuel consumption at part throttle type of events on it, because we're not applying extra clamp when we don't need it. Where the spring is always providing clamp, the helix only provides clamp when there's a torque being applied through it. The steeper angles and stiffer springs generally make the system numb to changes such as weight, temperature, and elevation. A lot of drag racers go about it this way with putting very steep helixes and very, very stiff springs on there. And it works pretty well for drag racing, but when you've got a lot of backshift events, it doesn't pan out that well. And you, generally speaking, having a lighter spring and doing more work with the helix makes for a lot better responding CVT system. And I mention this because you can get to acceptable tension ratios with springs and with helix, and they both add force on there, but it's a matter of making sure that between the two of them, you're in a state where you've got adequate margin to prevent slip, but you don't have a ton of margin such that you're losing efficiency. That spring, as I mentioned, the race is operating in all throttle events and helps responsiveness, but engine response is usually really fast relative to how fast the CVTs respond, unless it's like a turbo type vehicle. And like, do not use the driven to tune RPM. It's not meant to do that. It sets the tension in the system, and setting the correct tension is the foundation of the whole CVT cal. It's the base of the house. It has to be correct the first time or very close to it. Otherwise, you can't milk additional performance out of it. You can't tune yourself into being faster with the drive clutch. A real quick on why I talk about, like, spring dominated at the end and helix. This is just breaking out for one of our Polaris vehicles what the impact is of total clamp the belt is seeing as a function of the helix would be in green and the spring would be in red there. And it's relatively obvious that having a really stiff starting load on the spring isn't going to do squat for you in the grand scheme of things. Like a 20% stiffer spring still is just dominated by driven clutch loads when you're starting out. So you can't really get a stiff enough spring where you can be spring dominated at low ratio, nor should you expect it to fix problems if you've got slip at low problems. At high speed, though, the impact is about a 50-50 split on this particular application, and that's because of the significant reduction in torque the driven sees as we go from a 4-to-1 underdrive to a 0.6-to-1 overdrive. There's that multiplication of torque becomes you multiply by 0.6, so you don't even get as much torque from the engine at top ratio. So intended upshift, generally for peak performance, we want that baby flat, right at peak power on it. And the example of this Polaris Razor, that's at about 8250. And where I talked about that stall speed, there's a little transition on this initial upshift red line, kind of where this arrow is pointing. You'll see it changes slope a little bit, and that happens at what we would call stall speed. And if you look at a ratio channel, it's usually anywhere between like 2 times the theoretical to 3 times the theoretical minimum ratio. So 4-to-1 is the theoretical lowest ratio you could get. This is going to occur from about 12-to-1 coming in and exit at about 8-to-1. And that little transition, that stall speed, is going from dynamic coefficient on the belt to a static or quasi-static COF on the belt. And that's to be expected. If you have too steep of a starting angle on the helix, that tension ratio is too high, you won't see this type of behavior right away. And that can be okay, the belt is tolerant to that, but it just means there'll be a lot more slip on the belt, and you're not going to be optimized if you try to do like a drag pull type of event. And as we upshift there, we basically want it to be as flat as possible. There's some discontinuities that are to be expected. And then when we get near top vehicle speed, I should have noted this is engine RPM. As we approach top vehicle speed, it's not uncommon, and if you're optimized, probably okay to have a little bit of overwind at the end in this last where it's rising. That's a direct function of engine RPM, where we're just out of ratio and we climb RPM directly with engine speed. So this is kind of the characteristic curve that we want in a high performance Razor. It's the same thing you likely want in a Baja car, where we're trying to get as much performance as possible. Just instead of 8,200, we'll be desiring it to run at 3,000 or 3,200. So a couple questions, I'll answer that at the end actually. Drive clutch tuning. So if we have a driven clutch, we've calibrated our driven so we know that we're on the verge of slip, but we can't get the thing to slip. RPM needs to be reasonably close, but we don't need to worry about splitting hairs over small changes in RPM as we're calibrating the driven. Once the driven is locked down, that'll be the first parameter you lock and say we're not touching it. Then we go into tuning the drive clutch. And a lot of the questions about, what sheave angle do we use and what pins do we need to have? The sheave angle, a good way to look at that is going to be how much dynamic offset is acceptable on it, how much ratio do we need in the system. You can get most OE manufacturers are anywhere from 12 degrees on the drive to about 14 degrees on the drive. Not that that's magic, but it's a pretty small window, and any one of these I think could get you a pretty acceptable CVT cal. On driven clutches, they generally vary from 13 degrees to the steepest I know of is 16 degrees on the driven clutch. But really, any one of those, it's kind of splitting hairs at that point. Any one of those would lead to an acceptable CVT cal. The steeper it is, the higher that angle is, the more efficient it's going to be. Also, the more hub load you get, there's more tension between the pulleys that's required to prevent slip, which is going to be bad for bearing life in that. But any one of those will get you an okay clutch cal. It's all, do you want more ratio or do you want a little bit more efficiency? The spider pins is kind of like that. You pick one that works pretty well for us, and then you adjust the profile of the weight or the profile of the ramp roller assembly to meet that. By moving like spider pins in, we get a lower starting force. By moving them out, we get a lot higher starting force. And that's all really dependent on what your driven tension ratio requirements are on it. So if you have a lot of underdrive, it's going to take a lot more initial force because the drive can't support a very high tension ratio. But if you've got a lot less underdrive, you may be able to be down here where you don't need as much force out of the drive weights on it. And that's one of those kind of tunable parameters that the drive is just to get it to run to the right RPM. It's a dumb clutch. All it does is respond to the driven. F equals mr omega squared. It varies RPM to get the force to band-aid. To get the force to balance between the drive and the driven. Weight profiles, ramp rollers, again, once you have one you understand well, get that upshift curve like this, and if it's low, you should be able to understand what ratio it is based on engine RPM and a calculated vehicle speed, or if you've got a Hall effect sensor on a shaft in the transmission or something of the sort, you can know what position the drive was in there, and then just make an offset. It's just a squared relationship between force and engine RPM. Generally speaking, as you increase them for a given like profile or ramp, that'll shift that whole RPM up or down. Yeah, I got a cheat sheet on the next slide here. So if you want it to run 150 RPM lower throughout, just make a 3, 4, 5, 6 gram, whatever change that your calculator says you should have on it to the mass of it. And it generally shifts that whole force curve up or down. There's some things where it doesn't, but it's a pretty parallel offset. The spring it subtracts force from the weight, and it's kind of a band-aid for not having exactly the right weight profile selected on it. But if you're climbing in RPM or dropping in RPM, you can make some kind of minor tweaks to the spring and get pretty close to, or you can tip RPM up or down at high speed. The spring will not do anything really at low speed or initial RPM. It really is going to be a weapon that works for you when you get more than a third, half of the way through the clutch travel. The drive cheat sheet, curvature is the most powerful thing in the drive clutch. If you need to make it to run the right RPM throughout, you can't band-aid being high, then low, then high, or any other with weights or spring combinations. If it's not generally increasing or generally decreasing in RPM, you can't get there without making changes to the ramp profile or the cover profile or the drive weight. profile on it. You can't band-aid it into working. Mass, we talked about being more or less parallel offset. CG location, this is just that R on the MR omega squared on it. This is just if you move the weights outward radially in the clutch, or you move the center of gravity of the weight itself out further, it makes a pretty parallel offset. So for those of you using adjustable weights, putting screws or weights in the tip of the tail versus out front, it does move the center of gravity some, but it doesn't move it as much as you might think, because you're adding 5-6 grams to a, maybe say it's a 100-gram weight, you're adding 10 grams to a 100-gram weight. You're not really moving that CG much, and you're certainly not changing the curvature on it. So it doesn't make RPM really change a bunch at high speed or low speed with those adjustable weights. Spring rate, as I mentioned, like higher spring rates will increase RPM at speed, lower spring rates will drop it. And that's, again, a Band-Aid. If you see you pretty well like the profile, it's just it's generally increasing or generally decreasing, you can tip that up or down. I'll probably skip this one. This was going to be a few scenarios for what you might want to do, but in the interest of time and questions, I'll probably skip it here. So CVT design process, and this is also a pretty popular question of how do we get those points out of it. It's just exactly like the normal engineering process that we're looking for that Jason Fields is going to share about. And it all starts with, we called it specs this year, but it's really the requirements. What does the car need to do? And for the CVT system, we should cascade vehicle level requirements to the CVT system. So that's, you know, what does it need to do? Is there an RPM it needs to run at? Do we know how fast it needs to run? And under what conditions does it need to? Where's that power? Where's that torque? Do we know the loads going into the system? And top speed targets, is there a tractive effort target, an acceleration time target? All of those are going to be requirements that the CVT system is going to need to have. In addition to that, it needs to cool the belt maybe to below 270 degrees to avoid that type of performance variability, or it needs to stay below 230 to minimize degradation of that belt so it lasts a long, long time in the vehicle. But lay out, what are the requirements? What does it need to do? And how do we know that we're done designing the system when we get there? Research is super, super important. We really don't start a program without looking at other alternatives on it. And we should be asking ourselves, is there anything that we can do to be new or novel? And some of that research and development, maybe just characterizing belts better, characterizing the dynamic function of CVTs a little bit better. That's all research that can be done to speed up the design process and make the design more competitive. Then we step into design, and I kind of wrap design in and analysis get very closely intertwined on this. That belt length calculation is going to be needed in order to know how far to space the center distance of the pulleys. It's needed to know, how thick of a belt do we need, and that thickness will drive starting ratio, which drives tractive capability, which may drive gear ratios in the system on it. It's really not as easy as just picking a center distance in a belt and running with it. We need to look at how we optimize for ratios, and that may change from competition to competition. Shift, weight, ruck, pull, and puck calculation tools to understand force displacement is kind of upfront work. It blends design with data collection on it, but we need that in order to get robust analyses on the back end of it. Is there airflow calculations we can do? And then kind of lastly, and this goes into analysis, I should have dropped it there, is dynamic modeling of a CVT, which there's some questions here surrounding that's coming through on the chat. And it's extremely, extremely challenging to get a dynamic model of the CVT to behave well. I'm confident it can be done with some MVD like Adams car type tools, or you may be able to get there with a Simulink type model, but it is not easy. And I can't say that even we have a dynamic model that correlates out really well. It's close, but you wind up with a lot of assumptions on there, and it gets you certainly close, but it's not perfect by any stretch, and it doesn't behave as well. And a lot of that is due to that temperature and coefficient of friction variability of the belt. Uh, Data collection, more questions about measuring that belt tension. Load cells between pulleys are the way to do it, and you need a couple of load cells. You need to know the load between, you need to know position and torque, or you need to have multiple load cells in order to be able to resolve accurately what the top side tension to the bottom side tension is. The most accurate is going to be multiple load cells on a dyno to know what that belt pull is and to be able to resolve the direction of the pull between the pulley shafts. Everybody likes to do analysis. I'm not going to talk about that. Testing and validation, those slip models, understanding, going and testing a couple helix angles or spring tensions and trying to get slip to see how close our calculator is to predicting slip when it does, is an important part of the testing and validation on it, as is the new weight profiles. The first time you're out of the gate, you'll have something that runs probably not the right RPM everywhere, but we should be able to go back in and make a tweak, make a change to the weight and get really close that second time around on it. And data acquisition is a key part of that. If you don't know what RPM it's running at different ratios, you don't know how to change it. You're just flying blind. And you can start with a stopwatch and a tiny tack and a GPS. That'd be the minimum, but really getting something that can record real-time data is very, very critical to making that testing and validation and tuning easy and repeatable. And then finally, there's correlation of the analysis. So that's going to be your run on dynos, engine speed up. It's going to be acceleration runs. How do we match what we expected we would? Do we meet the requirements on it? Is there enough airflow? Is the heat rejection of belt temps as we expected? Did that second iteration behave as we thought? Did we see fatigue issues? Can we go and see if critical speed on that input shaft, do we tow a Baja car at high speed? Do we see resonance occur when we expected it to, or is it different? And for maximum points, we really need to do the entire design cycle of the vehicle in order to maximize the points there. And with a couple minutes remaining, that's about all I got here. I'll start answering some of the questions in the chat box here, and for sure keep shooting them on there. I'll stay on a little beyond here as well. One here is what software to use for dynamic modeling, and an MBD type software, they are all capable of doing it. If you don't already have those really solid calculation tools, I would definitely walk before you run and develop calculators for tension ratio and belt clamp in the driven clutch as a function of torque and belt length sizing on it. For sure, start there. Simulink is also capable of doing it. So it's a permutation of kind of those MBD type models or mathematical calculation tools. And I think any of them could get there. Some are probably better suited than others. Question about what should be the goal for the engagement RPM? Would it be at max torque? And that's going to go back to your requirements of the vehicles. As you increase that engagement RPM, the engine is running closer to peak power, so that transient time to get to peak power is less. So theoretically, your acceleration time drops. But that also means that you have a very high speed delta for the belt to make up between initial engagement to the time that it stalls. And high engagement speed can have a negative effect on drive-away characteristics on it, because you can't apply enough for, if you engage at, say, 1200 RPM, when you hook up to that load sled, you can build force as a function of engine speed squared from 1200 all the way to 3200. But if you're engaging at 3200, there's only a 200 RPM delta that you can increase in that squared relationship of force, so you may give up on tractive capacity. Low speed drivability, if you need to maneuver, handle, I know it's not super important for Bajas, but the ability to smoothly navigate obstacles also gets diminished. Range to use for belt COF, and what is a good way of measure it? A good way to measure it is cutting a section of the belt, applying a known load to it in between materials that are analogous or similar to your sheave surfaces, and then measuring the force it takes to pull it through there, both the breakaway static as well as the dynamic. And a puck of belt rubber sectioned out is a good way to measure it. You can't forget in your calculator tool, and it is in the kind of agricultural V-belts, they talk about it as well. There's a wedging effect that occurs that you can either use that wedge as a wedge effect, or you can modify the COF. And it's certainly better to do it with the right way with the wedge effect, but there is literature that does it both ways. If you're starting out a swag on it, it varies fairly significantly. Generally, belts are going to fall between like 1.1 and like 1.4 COF is kind of a range, but I would definitely have you measure it. As you get high loadings of fibers, sometimes that COF can drop down quite a bit too. It's highly dependent on the material of the belt and the fiber loading. If you are pushing temperatures high too, I'll note like doing it on a hot plate is important as well, because COF drops as temperatures get really high. It gradually increases, and at a certain point, it starts to drop off. Should we focus on shift characteristics or force balance models? The thing that's the most important is going to get that tension ratio correct on it. So not over clamping the belt is the most important thing. That's the foundation of all of it. And if you're over clamping the belt, there's going to be a ceiling always, and that ceiling of efficiency is based on how much tension you're running in the system. So you can go in kind of blindly, I would say, and get a drive clutch to run the right RPM. It's going to be a lot of iterations on it. But you can go in blindly and get something to be very competitive, but you can't get there if you don't have the right clamp associated with the clamp and you're not over clamping to begin with. Doubly why that's needed is for any of your FE, if you don't know how much clamp you're applying to the belt, what are your boundary conditions? How are you setting up sheave loads in there? Question about operating belt temperature and efficiency. That is a good one. I cannot say that I have looked at that. As I go through my head, as belt temperatures get hotter, they probably lose a little bit of efficiency because you're effectively over clamping them until you get to that point where COF drops off. So you may lose a little bit of efficiency, but you got to balance that with running an ultra cool belt is going to have a lot of pumping losses. In the case of like our CVT covers at Polaris, there's more heat rejection, more kilowatts of pumping losses in the system on some of them than what there is in belt heat rejection. So there's more work done in pumping air than we're removing from the belt. So you're also losing some amount of performance or power just in pumping air. Question is, did you say that center distance changes ratio available? Could you explain? Yeah, so you need to make sure that for a given center distance, you're going to have a ratio range that's available to it, and that's based on belt sizing and CD, and I forget which way it goes. I think the longer the center distance on it, you gain ever so slightly the ratio in it. What I was saying there more so is if you're using an off-the-shelf belt, you want to make sure that you have the right center distance selected to meet the ratio range requirements. So if you haphazardly throw together an 8-inch center distance and you throw an off-the-shelf belt on there that's too long, you're going to eat up most of your underdrive just by tensioning the belt, taking up that slack in the drive clutch as the sheaves are closing before you even begin to move, so you lose a bunch of ratio range. That's more what I was getting at, that you need to have the calculator to know what the center distance need to be in order to have the belt in the correct position when it begins to engage. How do driven loads affect CVT shifting? The methodology I usually think about with this is that the driven load just applies tension on it. It does affect shifting, but it's the drive that we should be manipulating in order to get it to shift properly. The driven we set to optimize tension. If we get, I'll go a few more minutes here. If we get cut off, I think it's supposed to terminate at 155 would be why. What are the things to look out for when one is trying to tune a CVT to downshift well? Shallower helix angles are going to be better, and to get it to downshift a lot better, you can play some trade-offs on there, and you can calibrate your CVT to be a lot lower in tension ratio, so we're artificially clamping it harder. And I'd recommend doing that with helix angle versus spring, but you can lose a little bit of efficiency, run a lot lower tension ratios in your system than what optimal would be, and get it to downshift better. And certainly, depending on what the requirements are of the vehicle, you may want to give up a couple % of efficiency on it and have a little better CVT cooling in order to get better downshift. As a good approach to CVT tuning is to equal the driver and driven forces applied on the belt for every RPM. It will automatically do that. There's a shift force, and that needs to be equalized in the drive and the driven, and the engine automatically will do that. The drive clutch will just run a different RPM in order to balance that. Our approach is going to be to get it to run at the target or desired RPM the entire time. So not the force balance should be to get it to balance at the correct RPM. Any tips on measuring belt tension ratio? That's going to be the load cell in between on a dyno between the drive clutch and the driven clutch. You may be able to get there with a load cell on a kind of overhung set of bearings to the outboard side on it. It's going to be difficult to resolve that to T1 and T2, the individual tensions, but you can make some estimations and get pretty close with known engine torques are just going to be what the delta is from those two. But with flexible shafts and overhung bearings and a load cell on the vehicle, you may be able to get a good idea of what the tension is in there. How to decide the sheave angle? We talked about that a little earlier, and it's going to be really dependent on requirements. Do you want more ratio or more efficiency? Narrow belt selection down. Again, per requirements, per center distances, per sizing of it, is what the belt selection is going to need to be. And again, kind of depending on how hard you're clamping it, if you're optimizing tension ratio, you can get away with very thin, flexible belts, which should be the target. Working temperature, less than 270 for a chloroprene belt to avoid wild COF variation. Less than 230 gets you, and that's belt temperature, not clutch box temperature. The belt will be a lot hotter than the air surrounding it. Should we prioritize center to center distance of off-the-shelf belts or tension? And I would say you need to make the design such that it's tolerant of that center to center distance, so that the driven is able to take up that. If it's a ½ inch, which is pretty poor, it should be able to take up that slack in the belt, if you will, without going bigger in the drive clutch. You don't really lose much ratio or gain ratio by going bigger in the driven clutch starting out. You will lose a lot of underdrive if you got a slack belt and the drive needs to take up that travel, because you get a lot of your underdrive just from that starting out small angle. Will using a variable helix angle benefit in any way? Absolutely. As you're trying to optimize tension ratio in the system, you'll need to have a variable angle helix in order to get closer to matching the optimal. Question about acceptable engine RPM overshoot. Again, it's going to be per requirements. In my experience, they generally accelerate best if you have a slight overshoot, slight being 100 to 200 RPM above target is generally the best, but you definitely, it's also not on a Briggs, not on a Baja either. And a study on what yields the best acceleration in the first 15 feet or 10 feet would need to be done to really zero in on what's the optimal overshoot. How to decide the effective diameter of the belt as sheave angle is different from the belt angle. Most everybody matches the driven clutch angle with the belt angle. And the reason generally for that is you get better belt support in the driven that way. But usually that's what folks do. And if you don't do that, the reason it's done is the belt wears to the driven angle typically. If you have a couple degree offset between the drive and the driven, it will over time become a lot closer to the driven angle than it is to the drive angle. And I don't know all the dynamics for why it does that. But because of that, generally everybody that I've measured competitively matches driven angles with the belt. How can we use 2 CVTs in series, and will it be able to use a greater speed range? Theoretically, yes, you could. The reasons to not do that would be really losses in the system. CVTs are very efficient at getting percentage of peak engine power to the ground, which is why they're so good. No other transmission type allows you to integrate the power curve. All of them, you're upshifting or you're driving, you just touch peak power for an instant in time, whereas CVTs, you're able to live there all the time. But unless you've got some just crazy high requirements for needing to have a large ratio spread on it, to get like attractive load capability, in a Baja, you're generally going to be best probably to have 1 CVT and a gearbox. And if you need more attractive capability, having a low gear set that's going to be 90% efficient is going to be better for vehicle performance. That said, I haven't done that, and it's one of those things that per vehicle requirements, if you want to have, a ratio spread of 25 without having without needing to shift, I don't know of a way to get there besides a 2 CVTs in series or a CVT and a shiftable transmission in series. So that there may be requirements that you have that make 2 CVTs in series the most attractive option. No, you're going to lose a little more efficiency. Your CVTs are probably going to tap out at mid 80% efficient through them. Would you have to construct physically larger CVT clutches in order to have a wider shift range? Generally, you do. The only way to not have to do that is to package that helix in unique ways. So we've been able to get a lot higher ratio ranges by pulling a bunch of overdrive. That's really the easiest way to gain ratio range. And packaging that helix smaller in the driven clutch lets you get more ratio range without getting larger diameter pulleys. And